Hey guys, welcome back to Chapter 6, Linear Graphs and Models. Today we'll be looking at exercise 6G1, linear modeling. So remember from previous exercises that the y-intercept is the initial value of something, and in our standard form for a linear equation we give that value a as our y-intercept. The gradient b is the rate at which y changes with every 1x. So remember that our standard form of the equation is y equals a plus bx, okay? As a worked example today, I'm going to go through question 1 from this exercise in your textbook. So we're going to do this one, well, I'm going to do this one for you, okay? And I'm going to highlight some things as I go just because you can do that if you like. So a tree is 910 centimeters tall when first measured. For the next 5 years, its height increases at a constant rate of 16 centimeters per year. We're letting h be the height of the tree in centimeters and time be t in years, okay? So all of that's going to be really useful, those values, in identifying what goes where in this general form of the equation. So the first thing you should do is decide which one changes with the other variable. Okay, so that's which one would be your y and which would be your x. In this particular example, the height is what changes over time. So height is our dependent variable. Okay, the tree can't grow if you don't give it time. And x is our independent variable. Okay, so I'm going to start my equation off in terms of h equaling something else. Okay. To continue with this form, I need to know what the y-intercept is now. So the y-intercept is the value when we first measure the tree. And in the first sentence, a tree is 910 centimeters tall when first measured. So we replace A with 910. Leave this for the moment. We'll come back to it. The number 5, I've just highlighted all of the numbers, okay? Its height increases, and the word increases is important because we know that we are adding, okay? We're growing the tree, so we should have a positive slope or a positive gradient at a constant rate of 16 centimeters per year, okay? And the time or the years is given by the value t. So we have it in our general form. The reason I start this number 5 here is that this rule will only be for values of t between 0, so when it's initially measured, and up to 5 years. Maybe it grows slower after that point, maybe it grows faster, we don't know, okay? But the important information here is that for the next 5 years, so t can only be between these two values, okay? Now for part B, we're going to sketch the graph, and forgive me because I'm doing this digitally, so it's not going to look very good, but we'll be fine. All right, we're going to sketch the graph. Remember that our first point to drawing a graph is to draw two axes and label them. Here we're going to label them T and H, okay? You might also choose to label, and I'm going to try and draw this on its side, this is going to be lots of fun, height in centimeters and time in years, okay? Optional extra, I would recommend it just because it's really good practice, but yeah. All right, our next step to drawing a graph is to put in our intervals. So we're going from 0, 1, 2, 3, 4, 5. And again, these values are really, really important, okay? Because that tells us what our x values are limited to. We're starting at 910 centimeters. And if I substitute in just for that last value so I know how tall my graph needs to go, 910 plus 16 times 5 gives me, I believe, 990. I think that's what I've got in front of me. Cool. And now we draw our graph. Now you could do this on your CAS if you wanted. All right, I'm going to go up to the top, so I'm just sort of going to put a point right about where it should be, which is about there. If it lets me draw it, and my initial value here. The important thing as well is that we can't go backwards in time. Okay, we can't time travel to before we planted this tree or this sapling, and we don't know the rate of growth before it, so we can't jump into the future. We only know the data that we have. So we connect those 2 points, of course mine's drawn very dodgily, but oh well, to give us our graph. The line in these particular cases will not extend beyond your start and end values, okay? So we have sketched the graph, and we give the coordinates of the intercept and its endpoint. You might label the endpoint here as 5990. However, the way I've labeled it is quite clear that this is the 5 and this is the 990. If I was writing this in my workbook, I would make sure that those graphs, or those lines here, these intervals, line up on one of the blue lines in my notebook. Okay. Finally, we're going to use the model to predict the height of the tree 4.5 years after it was first measured. So we're going to use this formula and we're substituting in for time 4.5 years. Okay, so we want to know what the height of the tree probably was at about this point here. Now, if you've drawn your graph beautifully, you might be able to read that off your graph. Mine is clearly not drawn beautifully, so I'm going to do this algebraically. The height of the tree would be whatever 910 plus 16 times 4.5 is. Of course, I'm going to put that into my calculator, or I'm going to check it off my graph. Okay, and I get 982 centimeters. So still a pretty tall tree. Okay, I mean, it was already 9 meters tall when we began. All right, so at 4.5 years' time, the tree was about 982 centimeters tall. That concludes today's lesson. As always, guys, if you have any questions, let me know. But otherwise, good luck with the work, and I'll speak to you all very soon.